Okay, now there are going to be two refractions that occur here. The first refraction occurs as we go from air to glass. Now remember from last time in class, that the index of refraction of air is about 1, and the index of refraction of glass is about 1.5. Okay, as I've said, you'll measure this later on this month in the mini-lab exercise. Now when the light first refracts here from the air into the glass, then the following occurs. So right here is our dotted line perpendicular to the surface at that location. Right here is the angle of incidence, like so. And recall one of the basic rules from Snell's law last time in class, that is when light refracts from low to high index of refraction, you bend towards the dotted line. The refracted angle is less than the incident angle. That looks like this. So right here is a refracted angle that is smaller than the angle of incidence. Now one thing to initially get confused on this diagram is to assume that this refracted light ray here is parallel to the base of the prism. No, that's not necessarily the case. And then right over here, we're going to have a second refraction, in this case from the glass back to the air. So right here at this location, this dotted line here is perpendicular to the surface at that location. This right here is a new angle of incidence. Call it theta incident prime. It's not necessarily the same thing as this angle over here. Once again, this green light ray here is not necessarily parallel to the base of the prism. But then, when the second refraction occurs, this is the other rule that we saw last time in class. In this case, the light is going to refract from glass, a high index of refraction, to air, a low index of refraction. When that happens, you basically refract away from the dotted line, so then therefore the final refracted ray looks like this. Right here is the angle of refraction. Call it theta refracted prime. Notice the large redirection in the direction that the light is initially propagating to when it finally emerges out the other side of the prism. So for example, if there was an object here like so, and then the light ray is coming off of that, by the time this light ray here emerges from the prism and say enters your eye over here, notice that you're looking in this direction like so. There's a large deviation here, a large angle like so, from the direction that the light was originally coming from to the direction that you're actually looking at, like so. So when you hold the prism up to your eye, as I indicated, and look at it, you can then see something that appears to be way on the other side of the room when you're looking instead in one direction. This is once again for now, ignoring the Roy G. Biv of color. Okay, let's take a look at a basic prism problem. Prism situations are very easy to describe mathematically. That's the following example. While you're writing the problem, let me kind of put into a box here Snell's law. There's a geometrical relationship from last time in class that describes the refraction. So let's see this big change in angle from the direction that the light is originally coming from to where it emerges out the other side of the prism. Basically what we'll do here is kind of work from the left-hand side of the diagram to the right-hand side of the diagram, ultimately calculating out here this final refracted angle. Okay, now we're given a couple of pieces of information here other than the index of refraction of the glass. Okay, first of all, we have this incident angle here given. Okay, the incident is equal to 30 degrees. And then we're also given the apex angle here, which describes the geometry of the prism itself. That's the angle phi. The angle phi is 60 degrees. And then what we're trying to find here, ultimately out the other side, is theta refracted prime. Basically what we have to do here is a quick three-step process. We do, first of all, a little bit of Snell's law to find this refracted angle here. Then we use the geometry of the prism to find this new incident angle over here. And then after that, Snell's law one more time to find theta refracted prime. Now when we use Snell's law, keep in mind that the left-hand side of it is describing where the light is propagating from, and then the right-hand side of it is what the light propagates into. So if I apply it then from air to glass, the left-hand side of the expression is going to be n for air, which is 1, multiplied by the sine of 30 degrees. That's our incident angle, like so. And this then equals the n for the glass, which is 1.5, multiplied by the sine of this refracted angle right here. So 1.5 multiplied by the sine of that unknown angle. And then just simply in degree mode on the calculator, we then figure out what that refracted angle is. So numerically, that works out to be the following. Left-hand side here is just sine of 30, which is a half, divided by 1.5, take the inverse sine of that stuff. And that comes out to be 19.5 degrees. Once again, however, this 19.5 degree angle right here, that's not necessarily the same thing as this. So we have to find this guy here by using the geometry of the prism. Here's how we go about doing that. The first thing that I calculate out here is actually this angle here in blue. Let's call this angle here in alpha. And notice that it's just a complement of the angle that I just found, theta refracted. This guy right here is 90 minus theta refracted. So alpha is 90 minus theta refracted. So it's 90 minus 19.5 degrees, which is 70.5 degrees. Okay, then next I use this angle here and this one. This is where the geometry of the prism becomes important to find this angle here. Let's call this angle here in blue beta. Recall, however, that the three angles in a triangle, these guys here, add up to 180 degrees. So I can figure out what beta is by just doing a little bit of subtraction. So the angle beta is 180 minus alpha minus phi. So there's specifically where the geometry of the triangular prism comes in. Yeah, I can't do this in my head, it's Friday. So 180 minus then 70.5, and then minus phi of 60. This is 49.5 degrees. And then we find now this theta incident prime. Notice that it's just a complement of beta. It's 90 minus beta. So theta incident prime is 90 minus beta, just plug in. So 90 minus 49.5, and then that incident angle now is 4D.5 degrees. Yeah, 40.5 degrees like so. And then we just do Snell's law here one more time. As the light now refracts from the glass to the air to figure out what this final refracted angle is. So now when I use Snell's law, the left-hand side is the glass and the right-hand side is the air. So for the left-hand side, we have n for glass, which is 1.5, times the sine now of this incident angle we just found from the geometry, 40.5 degrees, equals on the right-hand side of the expression n for air, which is 1, times the sine of this final refracted angle, theta refracted prime. So just multiplying it all out, 1.5 times the sine of that, take the sine, and you end up with a big angle. It's about 77 degrees. So you end up with this huge redirection of the light as it passes through a piece of glass where you take the sides of the glass and tilt them with respect to each other, in this case at a 50-degree angle. So the light coming from the object over here, if you're sitting over here, you're looking in this direction like so. So you can see this when you look through the prism at different angles. If you orient the prism just right, so you're basically looking at this diagram, you could be facing in that direction, but looking at something way over on the side of the room. Okay, now what about the colors? What about the Roy G. Biv? Well, that has to do with what is called dispersion. Okay, as I mentioned last time in class, the index of refraction for a material is the following ratio. Let me introduce dispersion to you by taking a look once again at this ratio. Now remember what the values here are. First of all, the numerator of the expression. This is the speed of light in a vacuum. No matter whatsoever, one of nature's fundamental constants, 3 times 10 to the 8 meters per second. Okay, the denominator of the expression is the speed of the light in the material, the glass, the air, the water, etc. As I mentioned last time, recall that light slows down when it passes through matter. The reason for that is because light is an electromagnetic wave, and the nature of matter is electromagnetic, so there's an interaction there, and it's this interaction that ultimately causes the light wave to slow down. However, how much the light wave slows down depends upon its wavelength. In general, the smaller the wavelength, the more interaction there is between the light wave itself and the matter that it's passing through. So compare 2 different colors, say blue and red light. Blue light has a smaller wavelength than red light. When blue light passes through glass, for example, it slows down a little bit more than red light does. The reason for this is because the shorter wavelength of blue light, as opposed to red light, ultimately causes it to interact with the matter a little bit more than the red light does. So if the speed of the blue light is a little bit less than it is for the red light, this means that the index of refraction for the 2 colors of light in the same material is not quite the same number. The difference between the 2 speeds, say for blue light and red light, is actually pretty minimal. So when I say that the index of refraction of glass is 1.5, it pretty much is for both of the colors, but not after you go out several decimal spaces. When you go out to decimal spaces of thousandths or 10 thousandths, then the numbers start to change a little bit for the 2 different colors of light. This is kind of a general rule associated with electromagnetic radiation. Basically, the longer the wavelength, the less it interacts with the matter that it's passing through, say blue to red light. Here's another example of that, say radio waves. Radio waves have a really long wavelength associated with them. Basically, the walls of this room are transparent to radio waves. The reason why is because the radio waves having such a huge wavelength compared to the atoms, for example, that make up the walls themselves, there's not much interaction that occurs there. So this is why everybody is able to, inside this room, receive a cellular signal, because the radio waves basically pass through the walls as if the walls aren't even there. Essentially, the walls are transparent to radio waves. But when you're talking about visible light, where the wavelength of the light is pretty small, it's comparable to the atoms and molecules, for example, of the material that it's passing through, then you start to see this difference in the slowdown of the light itself. So blue light slows down a little bit more than red light. This means that the index of refraction of the blue light is a little bigger than it is for the red light. So just briefly summarizing that here. So as light passes through matter, it slows down. But blue light, I'm using blue and red here for comparison, but blue light, which has a shorter wavelength, slows down a little bit more than red light does. Okay, red light has a longer wavelength. So because the blue light moves a little bit more slowly through the glass, say, than the red light, the index of refraction for blue light is a little bigger than it is for red light. So therefore, index of refraction for blue light is a little bigger than that of red light. Ultimately, what this means is that the index of refraction is a function of the wavelength of the light itself. It's only different, however, several decimal spaces beyond the numbers that I've been describing here thus far. So then dispersion through a prism ultimately is then caused by this phenomenon. That is, the index of refraction is slightly different for the different colors. And this then explains why a specific album cover looks the way it does. Jason, please put away your phone. I have an original pressing of that album cover, by the way, in vinyl. Hopefully everybody here knows what album cover I'm talking about. If you don't, there's a serious gap in your musical education. That's the following. And let's say that right here is our prism once again. Here's our apex angle. But now let's say that I have Roy G. Biv. Let's say that I have two colors of the light, red and blue. So here's red light like so, coming in along with, or here's blue light, coming in along with red light like so. The mixture of the Roy G. Biv is just referred to as white light. And then the two different colors here refract, but they do so at slightly different angles. So if this right here is my dotted line perpendicular to the surface, and now the index of refraction of the glass for the blue light is a little bit more than it is for the red light, when I bend these two colors here towards the dotted line, the blue light bends a little more. So then therefore, the blue light goes like so, whereas the red light, it still bends towards the dotted line, but just not quite as much, because the index of refraction for the red light is a little bit less than it is for the blue. So the red light basically does something like that. So we start to disperse the white light into its component colors. And then the same thing happens on the other side of the prism. Okay, right here is the dotted line perpendicular to the boundary between the glass and the air. And now when I refract the blue light here back into the air, I'll bend away from the dotted line, but I'll bend away a lot, because the index of refraction here for the blue light is bigger than that of the red light. So basically the blue light bends a lot, like so, whereas right here for the red light, this is our perpendicular line. When I bend away from the dotted line here, I just don't quite bend as much as I did over here for the blue light. But the red light basically does something like that. So by redirecting the light through this big change in angle through a piece of glass where the sides of the glass are tilted with respect to each other, then you can start to disperse the white light into its component colors. And then you end up with the Roy G. Biv. So, now this happens also when light is passing through an ordinary pane of glass, but when the sides of the glass are parallel with respect to each other, and the glass is thin, then you're not going to really notice the dispersion. However, even if the sides are parallel to each other, if the glass is really thick, think of, for example, this tank of water right here as a really thick pane of glass. At the right angle, you can start to see the dispersion even if the sides are parallel to each other. So if I look at the tank of water at just the right angle, I can see a little bit of the Roy G. Biv dispersion occurring. But it's not normally noticeable with just an ordinary flat pane of glass that's completely thin. However, with a large redirection associated with a prism, it's obviously very noticeable. And you can then just look at the Roy G. Biv coming from the ceiling lights or reflecting off of everybody here in this room. Okay, here's another example of dispersion. This is quite pretty. This right here is a pentagonal prism as opposed to a triangular prism. With a pentagonal prism, there's all sorts of crazy angles and directional changes here associated with the light, and the light very easily gets dispersed into its component colors.
Hi, I was wondering if I could give this to Natalie Menoff. It's really, you know.
Sure, she's right there in the back of the room. Go ahead and do so. Yeah, I'm going to pass this around the room. I only have one, so be careful with it, please. But take a look at this. Even if I just hold it out to you like that, start to rotate it around, you can easily see the Roy G. Biv, even from where you're standing, and it's simply because of all the crazy angles here, this redirects the light over enormous angles, enormous changes in angle. So take a look at this when it comes to you, it's quite beautiful. Okay, lastly about the basics here of dispersion, this is also important in an astronomical context in the following way. When we study the stars, for example, the only thing that we get from the stars is light. But the light from stars actually tells us quite a bit of information. So So what we do when studying starlight, for example, is we take the starlight passing through our telescope, and then we pass that light then actually through a prism, which then splits it up into its component colors. It splits it up into its spectrum. And then within the spectrum itself, we sometimes see what are called absorption lines. Absorption lines are dark lines within the spectrum itself where some of the light has been absorbed. That light being absorbed is caused by atoms in the star's atmosphere actually absorbing some of the light. This is one of the ways in which we figured out what stars are made of. Because when you look at the spectrum of a star and look at the absorption lines, it's kind of like a fingerprint. Different atoms absorb different wavelengths of color. So then therefore, when we look at those absorption lines, that then tells us what the star is made of. So this was first done starting over 100 years ago or so, because what we get from the universe is only light, but it does tell us a tremendous amount of information. Okay? That's the basics of dispersion. Okay, moving right along from there. Next we get to something involving refraction that is called total internal reflection. Let me erase all this junk. You guys know what Elton was, right? It's an easy way.
72.
Okay, it's called total internal reflection. Okay, I'm going to set up a refraction situation. I'll eventually demo this a couple of different ways for you. But I'm going to set up a refraction situation in the following way. Okay, here's a boundary between an n and an n prime. The way that I'll demo this initially is to have light pass from water to air, or alternatively from glass to air. So I'm going to set up a situation where n is greater than n prime. N for water is 1.33, for example, n for air is 1. So n is greater than n prime. Okay, and then let's just say we have an incident light ray coming in like so. Right here. And then right here is our angle of incidence. Now Snell's law then will tell us the following. Let's take a look at the expression. What I'm going to do with the expression here is cross multiply the n prime to the denominator here on the other side and write the expression in terms of the sine of theta refractive. Let's write it like this. Let me put that ratio of the indices of refraction here in parentheses. If light is propagating from high to low index of refraction, here in parentheses is a number greater than 1. So then therefore, if this number is greater than 1, n over n prime is greater than 1, when we then multiply it by the sine of an incident angle, this then means that the sine of the refracted angle is bigger than this number here. So then therefore, in other words, the refracted angle is greater than the incident angle, as we've already seen in a couple of other simple situations. Thank you. No worries. He's not here. He's not here. Probably an AP test. Okay. Please be careful with the prisms, guys. Okay, so as we've already seen, when you have light refract from high to low index, the angle of refraction is greater than the angle of incidence, and the reason for that is because this ratio of the indices is a number greater than 1. So in other words, I just bend away from the dotted line as we've already seen. Like so, right here is the angle of refraction. Now watch this. Imagine making this incident light ray come in at an angle of incidence that is bigger and bigger, like so. This then makes the angle of refraction bigger and bigger, like so. You eventually get to a point where the angle of incidence is at a specific value such that the angle of refraction is 90 degrees. When this happens, the incident angle is called the critical angle. Now increase towards a specific value. Called the critical angle. Critical angle kind of has a funny notation there. We call it theta crit. Okay, when that happens, the angle of refraction is 90 degrees. Such that refracted angle is 90. The situation looks like this. So take the incident angle from the diagram above, make it a little bigger. So the refracted angle gets bigger. If the incident angle gets large enough, this specific value called the critical angle, then the refracted angle is 90 degrees. It looks like this. Here's the boundary. Here's the n, n prime. The n is greater than n prime once again. And now I make my angle of incidence from the top forward a little bigger. Like so. And when I do, the angle of incidence is now this specific value called the critical angle, and then out the other side, the refracted angle is a 90-degree angle, like so. Light literally refracts along the boundary. There's a little bit of confusion here sometimes initially with the terminology. This is not the critical angle. The critical angle is the angle of incidence such that the refracted angle is equal to 90 degrees. Now here's just simply what it looks like mathematically. Let me get something to point with. On the right-hand side of the expression up here, if the angle of incidence is equal to the critical angle, this product right here is equal to 1, because the sine of 90 degrees is equal to 1. So the right-hand side of the expression for this diagram looks like this. Like so. This then means that the left-hand side, sine of theta refracted, is equal to 1, and the sine of a 90-degree angle is equal to 1. So theta refracted is 90. Like so. And now, do the following. Now take the angle of incidence and make it bigger than the critical angle. If you take the angle of incidence and make it bigger than the critical angle, this product here is now a number that is greater than 1. So now you increase theta incidence beyond the critical angle. When you do this product, the right-hand side of the expression is greater than 1. This then means that the left-hand side of the expression is greater than 1. Can the sine of an angle be greater than 1? Can the sine of an angle be greater than 1? No, it can't. So what happens to the refracted angle? It literally doesn't exist. Now, before I describe and then show you what this means, just look at the math. If you just look at the math, because this ratio is greater than 1, this then means that the refracted angle is bigger than the incident, the spatial diagram. If you increase this angle large enough, so it becomes this value called the critical angle, then this product here on the right-hand side of the expression is equal to 1. Therefore, the refracted angle is 90 degrees. If, however, you make the angle of incidence bigger still, then this product becomes a number greater than 1. So then therefore the sine of theta refracted is greater than 1, and then therefore theta refracted doesn't exist. So there's no refraction. So then what happens to the light? Well, all of the light, instead of refracting, it reflects at the boundary instead. And in other words, it stays in the water like so. No light refracts out into the air. That's why we refer to this situation as total internal reflection. Now, reflection occurs regardless, by the way, as to whether or not it's totally internal or not. So up on the top diagram, for example, yeah, some of the light here reflects at the boundary between the water and the air. This always happens when refraction occurs, I just haven't been drawing it as such. But remember our opening activity on waves back right when we returned from spring break? We attached two springs together, set a wave pulse down one spring. Some of the wave, remember, transmitted into the second spring, and that's the refraction. But remember what else happened? There was a little bit of a reflection as well. Same thing happens with light, I just haven't been drawing it as such. So then what does this situation then look like as a drawing? Before I draw it, Jacob, you had a question a moment
So
ago.
basically, all total internal reflection is just the point where all light will be reflected and not just some of it?
That's right, so all of it stays in the water as opposed to just some of it. None of the light refracts out into the air at all. So diagram-wise, that just looks like this. So this is the situation now called total internal reflection. So basically, take the diagram I just erased and make the angle of incidence bigger than the critical angle. So I'll exaggerate it. Looks like this. So once again, here's our n and n prime, water to air, so n is greater than n prime. And then we've got this incident light ray coming in at this really big angle, like so. So right here is the angle of incidence, and this is greater than the critical angle. The refracted angle literally doesn't exist, so no light refracts at all. All of the light stays in the water, like so, where this right here is the angle of reflection, not refraction, where these two angles are the same. All of the light stays here, that's why we call this total internal reflection. Now this initially really looks kind of confusing, but it's easy enough to demonstrate. So before I answer your question, let me just demonstrate it for you a couple of different ways. When I demonstrate it here, what I'm going to do is shine a laser kind of in this direction like so into the tank of water. When I do, however, this demo is kind of upside down from what I've been drawing, so let me just draw the demo first before I actually show it to you. Here's what the demo is going to be. Okay, so with this demo here, this illustration, I've got this water tank. Okay, so here's my tank of water like so. And then right here we'll say is the water line. This. And I'm going to take the laser and shine it from this direction. So, and now, yeah, when I shine the laser from this direction, it's going to pass through the glass. There's going to be a refraction from the air to the glass, and then from the glass to the water, blah, blah, blah. We'll ignore that because the glass is thin. We'll also ignore any reflection off the glass, et cetera, et cetera. The only thing that we're going to look at is right here where the light is incident from the water to the air. So we've got our n here of 1.33 for water, and our n prime for air equal to 1. So we're once again going from high to low index. And then right here is the angle of incidence like so. Notice it's kind of upside down from my previous diagrams. And then when the light does refract into the water, it will refract from the water to the air. Excuse me, it will refract with a bigger refracted angle, like so. And then what I'll do is I'll take the laser and kind of draw it in this direction like this and increase the angle of incidence. When I do, then the refracted light ray, well, that angle of refraction is going to increase. And then right at the right moment, when I get the angle of incidence equal to the critical angle, then the light ray itself, the laser beam, is going to be along the boundary here between the water and the air. And then if I take the laser and draw it in this direction further still, then I'm making the angle of incidence really large. If it's larger than the critical angle, then no light will refract into the air. It's going to stay internally within the water. That's why we call it total internal reflection. Okay, so now it just basically looks like this. I got to make the room really dark though. We'll get rid of this. We'll get rid of that. Let's get rid of that. Okay, here's my laser. I need a piece of paper for this too. Off. Okay, there's the laser now just so you can see the refracted beam here, let me put this piece of paper here towards the corner of the tank. So I'm gonna pull the tank out towards me a little bit, and I'm knocking it over, that would really just get that there. So, okay, then kind of let the water calm down here a little bit. And then I'll position the laser in like this. And then notice the laser spot here that you see on the paper. So the laser spot that you see on the paper, that's the light refracting out of the water then into the air. And then you can see the incident light ray, the laser beam itself, there in the water. And then if I start to pull now the laser towards me, I increase the angle of incidence. Once again, we're only looking to see what happens right here when the laser light is incident on the boundary between the water and the air. So if I increase the angle of incidence, then I increase the angle of refraction, and you see the laser spots start to move down towards the water itself, like so. And right about there, this right here is where the laser spot is basically on the boundary between the water and the air. So the angle of the incidence right there is then therefore about the critical angle. And now watch what happens then when I pull the laser towards me even more. Like so, and I'll exaggerate it. Notice that right here, no light is refracting out of the water into the air. It's all staying in the water. It's totally internally reflected. You can actually see the beams themselves, like so. Once again, if I push the laser away from me, now you can see the laser spot there on the paper. So now the angle of incidence right over here is less than the critical angle. Pull the laser towards me. Right about there is where I get the angle of refraction, about 90 degrees, right about there. So this right about here is the critical angle. And then go beyond that even still like so. Now the angle of incidence is a lot larger than the critical angle, total internal reflection. Okay, while I've got the lights off, here's another demo on this. Okay, I'm going to turn a bright light bulb here on my desk on. This is really bright. And these guys right here. These are fiber optic cables. The way that fiber optic cables work is by total internal reflection. So right here at the base of all of the cables bunched together, and these are, by the way, solid pieces of plastic. They're not hollow, they're solid pieces of plastic. And let me block some of the light. And then what I'll do is position it like so, and then take a look carefully here what you see emerging from the tip of each of the cut cables, a little speck of light. The reason why you see only light emerging from the cut ends as opposed to the side is because the light itself is totally internally reflected within the plastic. So then therefore it does not refract out into the air. You only see it emerge then from the fiber optic cable with the portion of it that has been cut. Now, obviously this is kind of pretty and kind of neat looking, but other than that, it's also very advantageous when it comes to the transmission of information. Really hot and bright. Okay, fiber optic cables have enormous advantages over copper cabling. Sending information down a copper cable faces a number of challenges. When you first of all send information down a copper cable as an electronic signal, well, the transmission speed of the information is much less than the speed of light passing through plastic. Okay, now yeah, light slows down when it passes through plastic. The speed of the transmission of the light itself is still enormous compared to the speed of electronic transmission through electronic cabling. And then secondly, with regards to electronic cabling, you also have to face the property that all cables have called resistance. Have you ever noticed that electric circuits heat up? The reason for it is because of a property called resistance. When electrical current is passing through copper, there's an interaction between that electrical current and the copper itself. Some of the energy is lost as heat. This is ultimately why all electric circuits heat up. When it comes to the transmission of information, that heat loss is signal loss. You're losing some of the information as the energy damps out as heat, basically. The amount of resistance associated with sending light down plastic, however, is next to nothing compared to the resistance associated with electronic cabling. So then therefore, there is not much signal loss with fiber optic systems as opposed to electronic cabling. And then third, and probably foremost, it's very expensive energy-wise, and it's very destructive to the environment to mine copper out of the ground and refine it. Okay, obviously we try to recycle it as much as we possibly can, but when it comes to manufacturing this fiber optic cable, it's actually pretty easy to do and it's relatively cheap compared to actually digging copper out of the ground, ruining the environment by mining it out of the ground in that manner, and then refining it, etc. That costs an enormous amount of energy and an enormous amount of money. So over the last couple of decades or so, basically worldwide, what we've been doing, the industrialized countries, is we've been ripping up all the copper cabling that has been there since the late 19th century, when it was first originally laid down, and we've been replacing it all with this, with fiber optic systems. Now, how many of you have fiber optic systems in your house? I have Fios. Do you have Fios? Or a version of it?
I think I have some version.
Yeah, I love it. Fios kicks ass.
Really fast.
You have Fios, yeah, it's lightning fast. You have Fios, you will never go back to anything else. Who here has Time Warner cable? Who here has Comcast cable? If you do, you have an electronic cable system. Okay, that technology is mature, so it works very well, but the download and upload speeds associated with it are not nearly as fast as a fiber optic system. Same thing with a satellite system as well. Upload and download speeds face some other obstacles that fiber optic cable systems get around. With respect to fiber optic cable systems, by the way, I have everything hooked up to a Fios system. My TV, my game system, all of my apps, all of my computers, my phones, etc. They're all hooked up to a fiber optic system. The download and upload speed times associated with Fios is lightning fast. I can download, for example, a 100 megabyte file, a typical audio album, in about 2 or 3 seconds. That's how fast the speeds are when you're talking about a Fios type of system. So if you have the means of being able to get a Fios system in your home, by all means do so. Fiber optic cables operate from total internal reflection. So it's basically just this. You've got a plastic strand like so. The index of refraction of the plastic comes from the molecular structure of the plastic. And then ultimately, when light is sent down the light pipe, as it's sometimes nicknamed, the angle of incidence here is just greater than the critical angle. So there's no loss of signal on the sound. Okay, Jacob, you got a question around
Well, a while ago, my question was, I noticed that there was this angle of reflection.
Mhm.
I think that would exist during all the other times we talked about refraction.
Yeah, absolutely. I just haven't been drawing it on these diagrams until now.
Would there
Now
be-
it becomes important.
Would there be a way to find out the angle of reflection and how much light is reflected off the?
Yeah, that's complicated electromagnetism, how much light is actually absorbed
more
by
horror
material,
stories.
how much is scattered, yeah, more horror stories, more detail at the end. Somebody else had a hand up? No? Okay, cool. Let's take a short break here.
Would you done the soup path?
Yeah, you do anything?
Can I pop that in?
I should, you go down, I should buy a bottle of water. I'll keep my car. Move over to the bathroom. Can you give me both a bottle of water? Two zeros.
Stay with me. Don't fade on me. Stay with me.
Mostly my other.
I know, it's a tough time. No, I kill it. Ask Miss Newville, fish tanks are really labor intensive. I got too many things. I have 2 cats. I have an Xbox One and an Xbox.
Yes! I can see it happening.
The only way it can happen is if I feel them.
I have a straight beat right now.
And it's weighted, right? I don't get me for Berkeley, I think it's
He's very screwed.
I'll take it.
Now he's driving.
Just to bring everything back.
Yeah.
It says Sadie, you actually have a single door, like you only a single girl, like you one girl.
I don't want to go to Calc anymore.
Single person. Oh, you're so lucky then.
I'm not sure I will have yeah, like good houses and
It's a small triple, it's like, it's like
Week
a
off.
toddler's room with 3 bunk beds in it.
I'm for sure not going Wednesday.
Be careful, by the way, when it comes to college roommates. My college roommate went to jail for 2 years.
My roommate date is like, I
Remember, I was-
have that next week Friday. I will have that.
Yeah, good. I mean, good.
So Monday, Friday, no math. I don't know about Wednesday.
I gotta get another one of these.
Oh, you got excuse? Oh, it's. Is that you got it? That's cool.
Civil War.
Is everyone
Good, where's
No, I think it's done.
He's taking a year off.
last year I go or like after this week I left.
No, I just. What was my first post?
I just don't even trust.
Yeah, but I should have done it this year, like pretty viral. After after math, and then section.
I didn't contact.
So I don't know actually.
We only did presentations and stuff.
2 years and
We actually learned from like that.
How we get along?
Like, I have to do something to keep myself awake. Like, I hate it when it just talks goes
Especially
on.
very soon.
I can't, like, I have to think.
When I take all the classes and dive
I
in.
can't.
The best is like the important.
There's a certain gentleman, you guys can enter the room.
Everyone.
Yeah.
No. No, he's not. He's like always in this side.
the first time.
My collection for is too large.
See diagonally.
The first day I walked in class, there were so many books because they were all movies. And I was like, there's so many movies. There are so many movies. And then like, a couple minutes later, I was like, look, it's good. First came in and awesome. And like, yeah,
They look like VHS
I mean,
boxes.
21 is
I kind of wish like it was
Take some drink.
thank you, sir. Thank you.
All right, take a seat, please. Okay, now initially total internal reflection sounds very confusing. But read all of it. As you'll see, it's actually quite simple. What we'll do essentially here are 2 things. First of all, I'll calculate the critical angle for 2 situations, one air and glass temperature. And then secondly, we'll revisit the prism once again to understand the other aspect of it. So I'm going to pass the prisms around again in just a few minutes when we get to the second problem. So take a moment to calm down. Don't worry, and then after this, I will show you lots of pretty pictures.
So Sean, does ultraviolet light pass release, like, is it really hard to pass through matter because of that blue-red?
Sometimes within the E&M spectrum, there are specific windows of opportunity, if you will, for kind of like the light to go in between the matter. So it turns out that because of the ozone in the Earth's upper atmosphere, which is O3, the atmosphere itself is mostly opaque to ultraviolet light. this is what then protects us, for example, from the ultraviolet light, which is quite damaging in terms of our cells and so on and so forth. X-rays don't pass through the atmosphere at all, however.